Wonder if you're familiar with the film True Lies, a movie with Arnold Schwarzenegger and Jamie Lee Curtis. It's a movie that was directed by James Cameron, and it's a great little action movie. But in this video, I would like to use a segment of that movie to show you how to solve a projectile motion problem and to really make an assessment of how accurate the physics is in a particular scene. If you're not familiar with the movie, there is a scene where the terrorist jumps off the married building, being chased by none other but Arnold Schwarzenegger on a horse, and lands in a pool on the other side of the street. Let me show you the video briefly, or at least a section of it. Okay, I'll just stop it there. And what I want to do is show you how to solve this, look at this situation and try to solve it in one of two ways. First of all, is it possible for this cyclist or motorcyclist to actually make the other side of the building? There are actually a number of good cues or clues in the video that gives us enough information to make that assessment. And secondly, if he doesn't make it, where would he land? But if he does make it, what speed would he need to be doing in order to make it? So let's have a look at the situation. So here's the situation, and as you can see, I have a simplified version graphic. I have, in this case, the motorcyclist jumping off the married building with a bit of an overhang over here. I have lanes of traffic over here and the building on the other side. And then what I have is actually three videos or three sections of videos that we're going to look at to establish some measurements. And I do this in my physics class. I explain the setup to the students and we collectively try to work out what the variables are. So let's break this apart and let's ask ourselves the question, can he make it at the speed that he's going at? Well, the first thing I do is I look at this particular image over here and I ask the students, well, how fast is he going? Well, before we start doing that though, let's first of all set up our data so that we know what all our data points are. I always tell my students to write down all the data variables that they can actually determine and to break them up into two sections. One is the vertical and one is the horizontal. And I always get them to write down all the variables. In this case, it's vertical velocity, final velocity, the initial velocity in the vertical direction, the acceleration, the displacement in the vertical, and the time. And then I ask them also to do the same thing for the horizontal. Now the horizontal is of course a situation, assuming no air resistance, that the velocity is constant. So in other words, we only have an average velocity that is horizontal, and we have a displacement which is horizontal, and we have a time. And of course the time in the vertical is the same as the time in the horizontal. So I asked my students, first of all, what do you think this bicyclist is actually going at? What speed is he going at? And we're usually looking at the video, most of the time we come up with a value of approximately 35 kilometers per hour. Now that's not an SI unit, of course, and of course what I do is then I convert that to meters per second, and for mathematical simplicity I convert that to a number roughly 10 meters per second. So the motorcyclist is moving horizontally off the ramp here at 10 meters per second. By the way, you'll notice that the glass shadows very nicely, not a cut on his body. The second thing we need to do is to work out, and I'll put this away, is to work out how far is it to the pool in the horizontal direction. And we need two video screenshots. And we do a bit of guesstimation. But the first thing we need to know is, well, first of all, we can see clearly that there are lanes of traffic here. And if we look very carefully, there are 3 lanes of traffic plus a sidewalk. And for simplicity's sake, we ask the students, well, what is that distance for each lane of traffic? Most of them predict that 3 meters is too large and 2 meters is too small. So we end up having 2.5 meters per lane. Now, considering there are 6 lanes of traffic, and allowing for approximately 2 lanes width for the sidewalk, we end up over here getting approximately 2.5 times 10, we get a 25-meter section across the two buildings. Knowing how big the figures are over here, and also this overhang, we make a guesstimate that this is approximately 5 meters. It may be more, may be less, but you'll discover that as we look at this problem. Some variance is not going to make a big difference. And this is 5 meters as well. So therefore the total displacement in the horizontal direction like this, we guesstimate to be approximately 35 meters. Now, that means the displacement over here is 35 meters, and we can put that information in. The next part is to ask ourselves, well, what is the displacement that he's dropping vertically? In other words, if this was the horizontal line here that is parallel to the takeoff point, and this ends up being the vertical drop down, and this being a right angle, this is the distance we want here, this Ry. And again, I ask my students, well, what is the angle of depression that he's looking at? That will give us some working out, because we've already established that this distance over here is 35 meters. So I get most of my students to work this out, and we all usually come up with a value of approximately 30 degrees angle of depression. It's not perfect, but it's a reasonable guess. Which means if we now want to actually work out the vertical displacement, you can see we can use the tangent formula to work out this displacement. And so in other words, if I use tan 30 is equal to this value divided by 35, I get a value in the order of approximately 17 meters. Now, again, for simplicity's sake, I'm going to make this 20 meters. In other words, what we're giving is basically the terrorist a little bit of an opportunity more to drop down. But for mathematical sake, it makes life a little bit easier. So now we have enough information, except a few bits and pieces here. The initial velocity, of course, here is vertical in the horizontal, and the acceleration is negative 9.8 meters per second squared. Now we can work out the time he takes to make the whole journey. And we start first of all with the horizontal. So as you can see, the time, if we work that out, the time ends up being the displacement divided by the velocity, which gives us 35 over here divided by 10. So the time of flight is 3.5 seconds. Now, of course, that is this 3.5 seconds as well. And so what we now do is we work out what is this true displacement given that this is our most accurate time. Now, of course, its true displacement ends up being ut plus a half a t squared. That's the formula. And we now substitute this in. We now have an initial velocity 0, so this becomes 0. This becomes plus a half. This is 9.8 negative over here, and we flies, of course, at 3.5 seconds. Let me get this to write properly. There we go. When we work that out, we discover that the displacement is 60 meters. In other words, if he's going to fly for 3.5 seconds, by the time he traverses the 35 meters, he has already dropped 60 meters. In other words, he doesn't land in the pool, but he lands way below the pool, another 30 meters below the pool. In other words, he's going to crash straight into the building. So the assumption that he's able to make it at 3.5 second flight is erroneous. He's not going to make it, not at least going at 35 kilometers per hour. Okay, so he doesn't make it then. So let's reverse the question. What if he does make it? In this case, what is the time of flight that he needs to be traveling, and what speed does he need to be traveling at in order to make it. And so we do the what if. Again, we use V, U, A, R, and T. And his final velocity we don't know, which we can work out in a moment. So therefore we're going to leave this as an unknown. His initial velocity is still 0. His acceleration is still negative 9.8 meters per second squared. His displacement now is this vertical, and we say he has to make it. So that becomes automatically 20 meters. Working this out, and I'll do the mathematics quickly, but you end up getting, using the formula R is equal to ut plus a half at squared, his time ends up being 2-second flight instead of the 3.5-second flight. Then what we say is, okay, what about the horizontal, sorry. And so his horizontal velocity now has to be a new value. He still has to make 35 meters, but he has to travel it in 2 seconds. So as a result, his velocity becomes 35 divided by 2, which is now 17.5 meters per second. Now to give you perspective, that means he's actually traveling at 63 kilometers per hour, considerably faster. Hitting this here at 63 kilometers per hour probably isn't going to be healthy for you. Then the final step is, well, what speed does he land onto the water? Well, the speed that he's going at is a combination of both his horizontal speed and the vertical speed. So let's now work out this horizontal speed. Vy is equal to u plus at. Now, initial velocity is still 0, his acceleration is negative 9.8, and his time we established as 2 seconds is equal to 19.6 meters per second. So in other words, he's traveling horizontally at 17.5 meters per second. He's traveling vertically at 19.6 meters per second. So his total velocity will be equal to a Pythagorean determination. In other words, he's moving horizontally at 17.5, he's moving vertically at 19.6. Therefore, via Pythagoras, we can work this out. He will have to be traveling this v, and I won't do the mathematics, you can do that yourself, would be ending up to 26.3 meters per second. 26.3 meters per second is equivalent to 95 kilometers approximately per hour. Have you asked the question, what would it be like hitting a pool at 95 kilometers an hour? Well, we can again work out what his acceleration is. If you looked at the scene, you'll notice he drops at most about a meter into the pool. So using v squared is equal to u squared plus 2ar, we can establish his deceleration. Again, mathematically we can work that out. The final velocity, of course, is 0 in this case. The initial velocity is this 26.3 meters per second, and his displacement ends up being 1. So his acceleration ends up being, and you can work it out yourself, ends up being negative 340 meters per second squared, or 350 approximately. In other words, what that means is he is experiencing an approximate g-force of 35 g's. Needless to say, his crotch would hurt. Anyway, it shows that James Cameron needs to have a physics lesson, but I hopefully haven't destroyed your enjoyment of True Lies. Go out and see it. It's a good fun movie, but just don't take the physics too seriously. Hope you enjoyed it.